Warm welcome to everybody to my presentation about a topic that is somehow pretty controversially discussed, not only in ISC SC77A Working Group 1, but also I think in the research community. Basically, this is a presentation that I gave in behalf of the SupraEMI project, which has certain universities and metrological institutions from all over Europe involved. So that's our university in Dresden. Then it's NPL, Deborah Ritzman, Stefano Lodetti, Paul Wright, and the University of the Basque Country, David de la Vega. As Angela has mentioned in the presentation before that there is a lack of interference cases, I basically decided, not only because of that, but beforehand, to start with an interference case in order to show you a little bit what is the challenge in the measurement of superharmonics. Imagine a public low voltage grid, as you can see it here in the figure. It is a transformer station on the right-hand side. Next to the transformer station, you have some slow chargers, which means you have the charger on the vehicle and not in the charging station, so onboard charging. You have about 60 meters of cable, and then you have another junction box, and at that junction box, a fast charging station is connected where the rectifier is located in the charging station. And we got a call of a utility, which was quite surprised that always in case one specific car has charged at the slow charging point next to the transformer station, there was a annoying audible noise of the fast charger when it was in standby mode. And for sure, those families having a flat in the apartment house next to that one has been a little bit bored about that. So what does that mean? In order to investigate that interference, we have to do some measurements. And I will show you quickly the results. What was the outcome of those measurements? The initial measurements have been done by the utility because mainly it wanted to identify the root cause of that interference. You can see here on the left side in that bar chart, phases 1, 2, and 3. Measured at the transformer station is the blue one, and measured at the junction box is the red one. And what is quite interesting is we measure at the transformer station only about 0.5 volts in each of the phases, while this is significantly amplified at the junction box 60 meters away downstream to up to a value of 2.3 volts. Okay, so we also did some measurements in order to validate it, but we used a different instrument than the utility. And this only shows the junction box measurement, but in a resolution of 200 Hertz bands, how it is defined or proposed in 61000-47. You can see now that at 10.1 kilohertz, we have somehow like about 1.7 volts, which is lower than what we have in the left figure, because of there is simply a different frequency band. And this might really be misleading, especially if it comes to the second challenge for the utility to compare actual grid levels with applicable limits like compatibility levels or product quality values in 5160. Yeah. So from that point of view, on the left side, it was a power quality instrument class A, but the method that has been implemented is not a normative one. Which brings us to the present state of standardization, where we recently received in 61000-2-2 compatibility levels for non-intentional emission. I will only cover in this presentation non-intentional emission. Intentional emission, like for narrowband power line communication, is on another sheet of paper. I will not address that here at the moment. So at the compatibility levels in 61000-2-2, they are based on the Cisper16 measurement method, because the only interest in defining the compatibility levels at that stage was to have some base values to coordinate equipment emission limits. And equipment emission limits are always measured above 9 kilohertz according to Cisper16. So big question now that arises, what do we do with grid disturbance level measurements? Because the utilities are used also to measure grid disturbance levels and to compare with compatibility levels. Yeah. The present edition of 61000-4-30 provides 3 indicative measurement methods for that frequency range. And I would like to introduce you quickly about what we talk here. There is the proposal for 9 to 150 kilohertz, just to take the actual informative method that is defined in 61000-47 Annex B for the 2 to 9 kilohertz range, which is in principle based on the DFT. You have a 200 millisecond measurement interval. You basically get then a 5 hertz resoluted spectrum, which you group into frequency bands of 200 hertz. You have a signal coverage of 100% without any overlapping between consecutive windows. There is another method which is much less computational, has much less computational burden, proposed in 61000-4-30 as I call it a new proposal, also based on DFT. You only take 0.5 millisecond windows, which means you get already the 2 kilohertz resolution of the spectrum. However, the signal coverage of this method, as you take only 32 times 0.5 milliseconds in 200 milliseconds, is only 8%. There's for sure then no overlapping, rather a gapping. And the last one is the Cisper16 method, which is established for lab measurements. We strictly speak about the Syspro band A, 9 to 150 kilohertz, where usually or originally a spectrum analyzer based on the heterodyne principle is defined, but it can also be done by digital implementation based on FFT. Here the measurement interval is 20 milliseconds. You also have a bandwidth of 200 hertz, but a signal coverage that is due to very, very high overlap, much higher than 100%. So let's see how those 3 methods compare for a typical signal from the field. What you can see here is a signal that we have measured in an installation of a PV inverter in combination with a narrowband power line communication system in Austria. You can see basically in the lower right figure, in the frequency domain, 2 distinctive emissions in that frequency range up to 150 kilohertz. It's on the one hand side the PV at 20 kilohertz, which is narrow and fairly constant over the time, and the power line communication system, which has a frequency range between 35 and 90 kilohertz. Yeah, you see it has typical 8 channels for the transmission, which is definitely broad with respect to the frequency band that we analyze, and it also varies pretty fast and significant. And if we now look on the different 3 different methods, you will immediately say there are differences, especially between the method B and the method A and C. B, just to recall, is that new proposal in 430. A is the method based on 61000-4-7, and the method C is the Syspro method with the quasi-peak detector. And while for the PV emission here in the middle to see, it seems that all of the methods are rather similar, at least in this logarithmic scale plot, especially for the broadband emission and the power line communication, they differ a lot. So now the big question arises, what is real? What do we need? Coming back to the assessment of that interference case that I have initially presented, you can see here reflected the values at 10 kilohertz for method A, 200 hertz bands at 1.6, roundabout 1.7 volts, and the 2.3 volts compared with the compatibility levels as they are defined in 61000-2-2 for non-intentional emission. And you can see it's well in the range, so it seems that the manufacturer of the equipment of the fast charging station is responsible to mitigate the problem. But imagine just 1 kilohertz lower, then it would be out of the compatibility levels, Yeah, it would be higher than the compatibility levels, and maybe the utility has to take action. So this sudden jump at 9 kilohertz here is only due to different impedances, so-called line impedance stabilization networks that are used in the testing. So, and from that point of view, a few open questions remain or can be raised. The first is basically a very general one. Can those compatibility levels that are defined in 61000-2-2 feasibly applied to grid disturbance levels as we are used to do it for harmonics, for example? And the second one for sure is, what is now a suitable measurement method? And this has, let's say, raised a lot of discussion, and it initiated this project SupraEMI. It's a pre-normative research project in the framework of Ampere in order to support the standardization with necessary input in order to develop such a widely agreed method for grid compliance assessment. We started our work in May 2019, and you can see again the partners of the National Metrologic institutes, the universities, and chief stakeholder, this is always required for such pre-normative research projects, is Michael Schwenke from Siemens. He is the convener of Working Group 9 at ISCSC 77A, which basically is responsible for the revision and the maintenance of 61000-4-30. Basically, this project consists of 4 working packages, but today I only want to focus on working package 1, which is this new normative method for the grid measurement. So basically, we want to compare the different existing methods. We want to maybe develop even a new or a modified algorithm and propose this to the working group. Later on, it's planned, as you can see, in working package 2, which is led by VSL from the Netherlands, a laboratory comparison of this new method and the existing method with different kinds of household equipment and even mixes of household equipment. How different are the results, especially with regard to Cisper16 and 61000-4-7 based method. In the next stage, we want to go to the field, comparing for exactly the same equipment, the levels that we can measure in the field to those that we measured in the laboratory. And last but not least, we want to do a set of grid measurements with regard to the network harmonic impedance that is seen by the equipment in order to verify if that reference impedance that is used for emission testing is, let's say, realistic. Yeah. So from that point of view, also for Angela, I think you can expect a few measurements of the network harmonic impedance up to the frequency of 150 kilohertz here. Good. Let's maybe look a little bit closer on Cisper16, because I would expect that most of the utilities are not familiar with Cisper16 at all, because this is strictly a lab measurement method with the only objective to protect radio transmission from interference. And radio transmission is usually not in the frequency range below 9 kilohertz, and even between 9 and 150 kilohertz, I believe it's not such a main issue anymore. Yeah, but explicitly no objective of the Cisper16 method is any thermal impact, as we have discussed also in the presentation, the webinar before, or malfunctions like flicker, like audible noise, and so on. Yeah. So this Cisper16 method is basically not only a measurement method or a measurement device, it's more a measurement system consisting of a receiver and a setup. And the setup includes a line impedance stabilization network, which is a symmetrical impedance between phase to earth and neutral to earth or ground. And especially if we look on the point of common coupling, where usually the compatibility levels apply, it's maybe questionable if this really is such a useful assumption. But this is something that we also want to explore in the project. The test of a EOT is an individual thing. It is very specific process where you start learning about the EOT by initial measurement. Then you try to manually search for the worst case operating point. The maximum value of the whole observation method is then compared with the limits. Yeah, and the question maybe arises: is a grid a similar thing like a EOT? The definition of the Cisper16 receiver allows a lot of flexibility in the implementation, which basically results in an uncertainty requirement of about plus minus 2 dB, which is in percentage, as I was also not really familiar always with dB values, yeah, is about 25%, plus minus 25%. So question is also, would you accept an uncertainty of plus minus 25%? And for sure, last but not least, a high computational effort. So having a closer look on those Cisper16, a few questions arise in our research team. So first of all is, how reproducible is the method? Second is, what's the additional computational effort that is required compared to the classical methods based on a discrete Fourier transform? And last but not least, exactly the issue of can a grid be treated as a EOT in the lab? How can we perform, or how continuous measurements should be performed? It's all about, let's say, aggregation times, yeah, which are not an issue at all in the Cisper16, because you just look for the whole cycle of operation of the equipment, and finally look for the maximum value of the quasi-peak detector. So how does Cisper16 work? You have to sample the input, so that's the digital implementation. Then you do a spectral analysis of a certain time interval, which is usually 20 milliseconds, but can also vary. Then you apply a window, for example, Lankos, or any window that is, let's say, allowed due to the requirements of the Cisper16 standards. Then you get basically an envelope of the amplitudes for each frequency, and the frequency stepping is usually 50 Hertz. Yeah, so you have 200 Hertz bandwidth with 50 Hertz overlap, which means if you would calculate the integral value, you would count a lot of energy twice or multiple times. Okay, now we have the envelope, and then the envelope is basically processed with a digital implementation of a quasi-peak detector, which is somehow like, as you can see in this little schematic below it, a little bit of filtering, let's say it that way. Then you have instrument finally, and also the inertia of the instrument has to be properly modeled. And then you get basically the weighted envelope where you take the maximum value as the value that you compare with the emission limits. NPL in UK has done a study about, let's say, the reproducibility. So how much flexibility, or using the flexibility provided by Cisper16, for generating about, let's say, or 360 compliant implementations by varying the window type, varying the overlap, varying the detectors. And then you can basically see exactly for the same signal that I have shown before, that for the PV as well as for the PLC emission, if we take one emission band out, there is a pretty large deviation. So 30.4% for the PV emission in the peak, and 42% for the variable PLC emission at, I think it's 54 kilohertz, or no, it's 60 something kilohertz. So from that point of view, that is well in the plus minus 2 dB uncertainty, but question is really, what is now the true value? Especially if you are close to the compatibility level, that would probably matter, because it will determine who is responsible to mitigate. Maybe briefly also to the computational costs. The Cisper16 method in general is much more time intensive, or has much more computational burden compared to the 4/7 based DFT methods because of this high overlap in frequency and time. So I don't want to go through the whole table here, but if you can see in the row that is highlighted, that the number of operations in relation to the reference that we have chosen here as the 200 millisecond method of the 61000-4-7 is more than 20 times. That's why usually the Syspro receivers are quite expensive. And the real question is, do we really want to have that on the network? Good. Last little issue that I would like to discuss is how to treat long-term measurements, how to cope with that. So the present methodology below 9 kilohertz for harmonics, or the emission in the frequency range 2 to 9 kilohertz, is in a way that you usually take 10-12 cycles, or the 200 milliseconds, then you do the DFT, and then you get consecutive values of the individual harmonics, as well as integral values, the Ph.D. Yeah? And then you aggregate it either in the 150, 180 cycle, or the 3-second values, and then in the next stage to the 10-minute values. And assessment is done for the RMS and the maximum value. And then basically, if you have a time characteristic, you can compare this with the 95th percentile for the 10-minute values, for example, or the 99th percentile of the time characteristic for the 3-second values. Very different to Syspro, yeah, where you have the 20 milliseconds, you have high overlap, and you only look on the maximum of the quasi-peak detector. So we tried also now to compare the different methods with regard to the aggregation characteristic. I don't want to go through all those numbers on the slides, but what we did is we analyzed about 25 minutes of the field measurement signal that I have introduced at the beginning. And just to have as reference, so all the values here are in millivolts again now in the table, and the deviation range from the Cisper16 implementation is 16 millivolts. Yeah. So, and we have on one side the quasi-peak detector, we have the 4/7 method using RMS values, and the 4/7 method using the maximum value in the 200 milliseconds. So from now, now you have let's say the 3-second values as aggregated values, and as aggregation you can either use the RMS value, or you can use the maximum value. What would that mean? If you have those 15 200 millisecond values, which will be aggregated to the 3-second value, you can either use the RMS of the 15 values, this is the blue value, or the maximum of the 15 values, which is the red one. And if you have a look on how the Cisper16 compares with the IEC 4/7 for the RMS, and the maximum is pretty close to each other, which maybe raises the question, could we maybe even use the 4/7 method as a good estimator? But this is, let's say, still requiring further research, because this is only for this specific PV signal, which is fairly constant. So we also have to apply it for other types of measurements. Another interesting question that has been risen is the need of integral values. At the moment in Cisper16, or even in the limits that exist for lamps and for induction cookers at the moment, no integral limits exist at all. But we are used to have integral values as valuable and important indices, which represent somehow total energy, total signal energy. We also talk about partially weighted or weighted indices. But this is all, let's say, not so easy with the Syspro method because of the high overlap. which means you have to modify or adapt it in order to compensate for the overlap. And for the Cispre quasi-peak, this is done by a so-called correction factor, which depends on the window that you use, window type, and the overlap. And recently, in a joint working group developing the emission limits in the frequency range 2 to 150 or 9 to 150 kilohertz, they also introduced informative, or want to introduce informative, I have to be careful how I say it, an integral value based on Cispre average using a fixed overlap of 50% and a reduction of -3 dB. So this sounds to me also somehow like experimental found, and not really thorough, let's say, systematic proven. Yeah, but at least it should work for most of the equipment. And if you apply now those integral values, this adapted Cispre methods, and compare it with established value that we usually use today, which is based on the, let's say, 4-7 method, you see that there is in the unaggregated 200 millisecond values, if you do statistical analysis, quite a lot of differences. So with the 4-7 method being in the middle. Good. That brings me now to the conclusions, and I think that's also the time, Thijs, to maybe start the poll, because I would be really curious about your opinion about certain questions, which are a little bit linked to those that you find here on the slide, but I formulated it in the poll a little bit, let's say, different. Yeah. So first is what accuracy and reproducibility is required for Class A instrument. So the view of our project or research team is somehow 25% seems not really feasible. We should go below to 5 to 10% maybe. Yeah. Second is what indices are really useful in such a normative measurement method. Is it only the quasi-peak value which is then compared with the compatibility levels, even if we do not really know if that is feasible to be applied to the network? Or should we also have RMS and maximum values along with that? Yeah. Should we have only individual frequencies? Should we also have maybe integral values included? Is another question. Yeah. And for sure, what about currents? Currents are quite important in my opinion, and that has also been shown by 430 development, where in addition 2, currents has been introduced informative, while in addition 3, they became normative. So why not also already considering currents? But Cisper16 doesn't deal with currents at all. So what should we maybe require from working group 8 to give additional guidance on how the compatibility levels that they have defined in 61000-2-2 has to be interpreted with regard to grid measurements? What aggregation
Jan,
methods?
the results from the first question are in. The others questions are still on hold. First, you can react on the results from this question.
Okay, so we have to always look individual to them. Can we not look at the very end to all of them?
No, that's an individual thing indeed. Yeah.
Can you? So okay, good. Then maybe we have to go to that. So where can I see that? De Paul.
Sorry. Okay. Okay, you can. Yeah, you can open up the polls menu on the right. There you can see the results of the poll that's going on now.
That's the only thing that we didn't try. The poll, I cannot see the polls. Maybe you can just tell maybe about the first one. Maybe question and answer. Thijs?
Yeah, the first one at about 80% count of no. So most people voted no there.
Okay, so this was the question about the accuracy. So, okay.
Yeah. So this second one, do you think that the compatibility levels based on Cisper16 must be strictly applied to grid measurements? Well, we've got a bit of a tie here. There's 32% saying yes, 26% saying no, and 42% is not sure.
That's exactly the same situation like I think in working group 9.
Okay, excellent. And we just started the third poll. Would you expect from an instrument that it provides more than only quasi-peak compatible values?
So that's a little bit related to the second question on the slide. Yeah, what indices should really be reported?
Okay. Well, a lot of people are voting. We're almost at 50% of people voted. Oh, we just passed 50%. And yeah. So we eventually have 80% of people voting yes, 4% no, and 50% not sure.
Okay, excellent. So this is definitely important. Even I will basically take the answers to the poll, also to the working group 9, in order to give also a little bit of feedback from basically those that have to apply it later. Yeah, because especially this discussion about should we also report RMS and peak value has been very controversial discussed, at least in the last working group 9 meeting.
Okay, excellent. The fourth poll just also started. Should a normative method also provide time characteristics in addition to the yes-no decision on compliance? A lot of people are voting for this one too. Again, almost at 50%. And I do also see a question in the chat of how to vote. It's actually just clicking the yes, no, or not sure box, and that should work.
So it only are 6 questions if someone is curious how long this will go.
Already at number 4. So, well, again, most people think yes about this question, about our answer about this question. 77%, 7% no, and 17% is not sure. And Tim just started the next one. Number 5, would you accept a measurement method that might not strictly be Cisper16 compliant, but provides an acceptable estimate?
So this is basically linked to the third question here on the slide. Yeah, if there is maybe the option to have a simpler method, which maybe together with a conservative translation factor can provide some good estimate, at least for a class S instrument, for example. Otherwise, we have to expect that the costs for power quality instruments will significantly rise, in my opinion.
And I think a lot of people agree with you, because I see a lot of people are voting yes. So 87% even votes yes on this question, 3% says no, and 10% is not sure.
And the last one.
And there it is. Should a new normative method also cover the measurement of currents?
This is linked to what I tried to explain in the second question on the slide.
Okay. So again, a lot of people answering yes, 85%, 15% not sure, and actually nobody voted no. So apparently the currents, measuring the currents is seen as very important.
Okay, at least that confirms a little bit also my position, because I intentionally, let's say, ask the questions in a way that first answer basically is always the one that I also prefer. Yeah, except so for the first, according to the regarding accuracy, if the 25% are acceptable, for sure no, in my opinion. And this also reflects the opinion of the SupraEMI team. So this is very valuable. Thanks a lot for voting. I will definitely take this result also to working group 9, and let's see what happens with that. Okay, so I'm almost finished now. So as I expected the poll working a little bit different. We are a little bit behind time, but the last what I would like to share with you is I started with the interference case. I would finish with the interference case, and I want to share that because this is exactly one that Matt has already mentioned in his first presentation. Yeah, it's about the coffee. Yeah, so there was suddenly coming up customer complaints in a small town close to Dresden, and one was that the coffee maker grinds the coffee, it throws it away, and lets out water. It's not even tea. Yeah, it's just water. Yeah, and what was also quite funny, at least for me to hear, because I was not affected by it, was that a hairdresser saloon, the lady was totally crazy because their hair dryers turned on and off itself 40 times a day. Yeah, which was totally ridiculous. And I don't want to go in too much detail, but you can see basically in the right lower part the layout on the screen. And finally, it turned out when we did the measurement in point 3, which is pretty, let's say, at the end of the feeder, that a CNC mill has been installed without any EMC filter, and it had a significant emission at 8 kilohertz up to about 3 volts. Yeah, and if you think about or remember the compatibility levels, yeah, 3 volts at 8 kilohertz was definitely well above the compatibility level, which means that is something that the customer has to mitigate. Yeah, good. Because we are quite a bit behind the time, I would like to finish here at that point. Would like to thank you a lot for your attention, and I would like to show maybe that little slide at the end to give a flavor of our activities that are also mainly focused on measurements, low voltage, the laboratory, in the grid. But surprisingly, nowadays, at least in Germany, the transmission system operators have rediscovered power quality as a topic for them, and we have even certain projects running with them at the moment. Thanks again, and yeah, feel free to ask questions, and what we do not manage, you just can forward to me as well, and I can then also respond by mail.
Oh, thank you, Jan. That was very interesting presentations. Indeed, all the questions will also be logged and will be sent to you afterwards. So even if we can't answer a question now, it can be answered later via email. But well, we do still have some time. So let's see. We have one from Vladimir Chuk, somebody you know well, of course. First, he says hello from Eindhoven. He's looking forward to the coming results of the research on the compliance impedance to be used, and he asked the question: should we perhaps think about the same question for below 2 kilohertz range, as the 61000-3-2 standard requires a clean voltage in the test, which also often leads to under or overestimation of emission?
Well, that's a good question. So hello to Eindhoven here from Dresden, Vladimir. The question is indeed a valid one, but I think you have to look also a little bit on the history, how the emission limits have been established. And basically for classical line commutating equipment, yeah, no impedance and sinusoidal voltage is somehow like a worst case, yeah, which will cause highest emission. Yeah, if we let's say exclude pointed top can even have cause higher higher current harmonics. Yeah, and this is probably the main reason why no impedance has been used for the 2 to 9 kilohertz range. An impedance is proposed, but anyway, I think 61000-3-2 maybe needs some kind of revision in order to take the modern equipment properly into account, because all the modern technologies, self-commutating technologies, for them, for sure, sinusoidal voltage is not really the worst case anymore, because they seriously react or react sensitive on voltage distortion, yeah, distortion from the grid.
Hey, well, excellent. Thank you for that question. Sounds like the standardization committees have a lot on their hands. Another question, or more a discussion point from Amir Broshi. He says, I think that the measurement resolution, accuracy, etc. depends on the solutions. Measurements are for solving issues, not just for information. It's more a little bit of a discussion point, I believe. Maybe you can comment on that.
Yes, so the big discussion in working group 9 with regard to the method is exactly in this direction. Shall 61000-4-30 provide also a normative method with regard to troubleshooting, or as it is a standard, should it strictly only introduce a method that can be used to do compliance assessment, which means comparison with compatibility levels. So definitely what I want to do has a main impact on what I have to measure and how I have to measure it. But in my opinion, there is still added value to have some kind of a normative method that is beyond the compliance assessment, because otherwise all the other measurements that people will do will either be not comparable at all, or everybody has to implement something on their own, which is also probably not the idea. Yeah, I hope that answers the question more or less, or it's kind of a viewpoint. Yeah.
I hope to. But let's go to the next one from Jill Sutaria. How can the presence of different EMC filters influence the measurement of superharmonics?
Well, they will definitely influence it. We have impressively seen it in the presentation in the morning, yeah, that the impedance, especially the ratio of the impedance between the grid side and the equipment side, will have a significant impact on the current voltage condition at the particular supraharmonic frequency. EMC filters in devices that are in the grid will for sure change that network harmonic or that impedance seen by that single device. Yeah, and from that point of view, they will have a significant impact. On the measurement method itself, I'm not really sure, because I can measure it and the values will change. Yeah, but that we have to take that into account when designing the method, I don't see that at the moment.
Okay, thank you. I had a question myself too, by the way. In work package 2, the laboratory comparison of the new methods and the existing methods, you told they were measuring household equipment over there. And I wondered, do you consider an electric vehicle nowadays to be a household equipment too? Because, well, you charge it at home.
Yes, so maybe it's a little bit more broad than strictly only household equipment. So as far as I know, we are not so much involved in working package 2. So Helco could probably tell more about that, because VSL is leading it. But as far as I know, at least an EV as well as a PV inverter for rooftop use is included as well, because in my opinion, electric vehicle chargers, they are the most severe sources of superharmonics at the moment. Even PV inverters have much less emission usually than some of the EV chargers. Yeah. So we measure, so we talk not about, let's say, 0.0 milliamps anymore. There is one specific charger which can easily have about 2 to 3 amps at 10 kilohertz flowing between the different vehicles, and even several amps in the grid. Yeah, so that's definitely for sure, and that will be included as well, as far as I know.
Okay, that's good to hear. And also we received a question from Tim. Do we need to worry about damaged equipment due to excessive supraharmonics? And what will happen when we do nothing?
Well, we also, let's say, discussed a little bit about the interferences in the first webinar today. Indeed, the supraharmonics are more an issue of equipment interference. I fully agree with that opinion from the morning, where you have to distinguish between malfunctions and additional thermal stress. Malfunction usually is represented by flicker in lamps, or audible noise, or maybe even equipment damage, as you say. However, a real immediate damage is something that I did not experience. Well, only one time, but that was when a student, instead of, I think, 1 volt, outputted 50 or 100 volts at the supraharmonic frequency accidentally to an equipment. Yeah, but this should not count. And the thermal stress is linked to the increased aging, so lifetime reduction, which in my opinion is also very important and serious, because this is usually not addressed by any of the immunity limits. Yeah, they usually look only on malfunction. So immediate damage, I would say rather rare, except you have really high levels, but definitely interferences and maybe early fail because of lifetime reduction.
Excellent, thank you for that elaborate answer. Well, one final question from Angela. Angela Espin Delgado, we've seen this morning presenting. How to treat cases in which two equipment interact, creating beating frequencies that lead to problems. Have you observed these cases in the field?
Oh yes, oh yes. There was a really beautiful and nice case in Switzerland, where a lady working in an office building called the utility and told them, my green energy is making noise like a cricket, so it's chirping. Yeah, I cannot do that here, and especially because this is recorded, I will not do that. Yeah, but you can maybe imagine there is a sound that will change in, let's say, noise level. Yeah, in loudness, from being really loud down to almost nothing. And this is somehow like such a chirping effect. And this was basically caused by two UPS systems from the same type, with in fact the same or almost the same switching frequency, which resulted exactly in such a beating effect. Yeah. And we have also seen such a beating effect in this central charging infrastructure that you see on the right bottom, on the final slide, if you can still see it, where you get really serious beating between 0.4 and 2 amps or something like that at 10 kilohertz if you connect two cars. If you connect more, then the beating will somehow, like, how can I call it, a little bit somehow averaging. Yeah, but the beating can also cause really interferences. Yeah, that's true.
Yeah, excellent. Thank you for that answer. We've actually seen the same during our measurements, also with the beating effect. Tim, we will be presenting at 2 o'clock. We'll also elaborate on our findings among those beating effects. But first, at 1 o'clock, Vladimir Chuk will be presenting. I would like to thank you all for joining this webinar, and hopefully we'll see you in the next webinars. And don't forget, we've got a panel session at 3 o'clock, which you all are invited to join. If you need to register for it, just go to our web page. In the news section, there's a news item on this event where you can find the schedule and you can register for the panel session at 3 o'clock Central European Summertime. Well, thank you, Jan. And
thank you to Eilert to organize that beautiful and interesting event in this bit more difficult and sometimes boring times in home office. So I really enjoyed it.
Well, you're more than welcome, and to all the attendees, you're more than welcome to join too during the other sessions and maybe during our next event, because well, we've got a hang of it. We like it, so we will be doing it again.